Good morning. I'd like to commence by acknowledging the traditional owners of the land upon which we meet today. I pay my respects to their elders past, present, and future. Thank you. Gentlemen, if you could please introduce yourselves and explain who you're here representing today. Thank you.
So I'll start. My name is Paul McDougall. I'm representing the Schlumberger Australia land business.
Thank you.
Good morning. My name is Joe Lima, and I am the Director for Environmental Sustainability for Schlumberger. It's a global position, and I'm based out of the U.S.
Thank you.
Good morning. My name is Kalinin. I'm representing Schlumberger Australia. I'm in the field of hydraulic fracturing stimulation, based in Brisbane.
Thank you very much. Thank you. Whenever you're ready. Thank you.
Okay, again, thank you to the panel for availing of this opportunity. We were a bit late getting our corporate permission to do so, but again, thank you. Again, I'd like to acknowledge the traditional owners of the land where we are, and also the basins where we operate in Australia, and their elders past, present and future. And I'd also like to thank the panel for the body of work that you've done in the interim report that has been published. We're very appreciative of that work, and the torrid schedule that your community engagement, you've availed the population of the NT with getting that communicated. So I appreciate that very much. And also thanks to Joe, who has travelled a long way to be here today, and I'll hand it over to Joe to take it from here.
Great. So if you don't mind, I would like to share some slides with you to kind of give you a little bit of my background, but also our experience with the unconventionals.
Thank you.
Shift F5.
Just one second while I get the presentation happening.
Let me begin. You can tell we're experts on oil and gas, but not PowerPoint.
That's good.
It's giving me great confidence, gentlemen.
Great. So I somewhat struggle with what to title this presentation, but just decided to look unconventional reservoir development, since that is, I think, what you're trying to understand. Just a little bit about Schlumberger. So Schlumberger is the world's largest oil field service company. We employ around 100,000 people, and we're working in over 85 countries worldwide. From a technology perspective, what we provide to our customers, we like to refer to it as a pore-to-pipeline perspective. So basically the things that you do to extract oil and gas from the ground and bring it up to the surface. That being said, essentially all places where oil and gas is being developed around the world in one way or another, Schlumberger is interacting with those reservoirs. We have facilities, again, in 85 different countries. We have employee nationalities totaling about 140. Our company is 90 years old. We were founded in 1927. And what you see on the bar graph here is basically the history of how Schlumberger has grown to be where we are today. We started out as a wireline company getting measurements of the reservoir rock, and we've progressed from there. One of the major companies that we acquired was in the 1960s, Dowell, which is where our pressure pumping experience, hydraulic fracturing, cementing, and so on came from. I draw your attention to the center of the screen there, the graphic in the middle. We believe in reinvesting into research and engineering. Since 2011, every year we have invested over $1 billion US in research and engineering. And so this is technologies to further the things that we're delivering to our customers to help them extract oil and gas out of the ground. And throughout my presentation, I'll talk to you a little bit about the application of these technologies in an effort to more efficiently and safely help our customers produce hydrocarbons. So before I get too far into that, I'd like to give you a little bit about my experience, my personal experience. I'm a petroleum engineer. I've worked for Schlumberger for nearly 30 years now in various roles, so engineering roles, management roles, and so on. Prior to the role that I have today, I worked on Schlumberger's green chemistry for fracturing fluids. And I also am the architect behind our chemical disclosure process, which has ultimately been adopted by Frac Focus as being the standardized process. So now that being said, I'm going to go ahead and delve into the unconventional somewhat. I don't know if you're familiar with the concept of a resource triangle, but the graphic you see on the screen basically is saying that the high quality rock where oil and gas would flow naturally and so on is small in quantity. So you look at it at the tip of the pyramid and its base across the bottom of the triangle is fairly small. As you move down into poorer and poorer quality rock, we end up with much more of that available to go out and produce hydrocarbons from. It is obviously the gas-bearing shales and oil-bearing shales where today most of the focus is on the unconventionals. Now, the definition between conventionals and unconventionals essentially is that you have to stimulate the rock in order to make it produce. But as you move down the triangle, your F&D, or finding and development costs, increase. You have to put more technology in order to extract the hydrocarbons out of it. So it is something that has become more of a challenge to work in those types of environments. Now, going back quite some time, looking at the evolution of the reservoir rock, obviously we're extracting hydrocarbons from organic matter that's been buried in the earth. Typically, geologists and geophysicists would be looking for structural traps, places where oil and gas would accumulate. They would end up with to some degree, impermeable barrier where the oil and gas would accumulate. They would identify those, and then they would drill to that. And this would be closer to the top of that resource triangle. This is before hydraulic fracturing was really being deployed. And hydraulic fracturing, even though it's well documented that it's decades old, realistically, hydraulic fracturing hasn't been applied in large scale into the late 1980s and early 1990s. It is in that time that our customers were drilling into tighter and tighter rock. Most of that was sandstone. And so the wells that were being drilled were typically vertical wells. But as you were moving down into this tighter rock, you needed to have more wells in quantity to achieve the economies of scale. Then come about 12, 15 years ago, the combination of horizontal drilling and hydraulic fracturing, but multi-stage hydraulic fracturing. In other words, breaking a horizontal wellbore into smaller sections and stimulating it in a discrete manner. That has ultimately allowed us to economically produce from that very tight rock that's at the bottom of that triangle, the shales. But I'd like to emphasize that it's a combination of existing technologies. So directional drilling's been around for quite some time. Hydraulic fracturing's been around for quite some time. The combination of these two things has enabled it to happen. There were some technologies that had to be filled in. So how do you effectively and efficiently break up a horizontal wellbore in order to be able to stimulate it? But it's that type of development that allowed us to work in the unconventionals. So why does hydraulic fracturing work? And why does hydraulic fracturing in combination with horizontals work? It's all about surface area. And so in this case, I have three different examples to show. So on the upper left is a vertical well that's drilled through a 60-meter high reservoir rock. And without stimulating that, the surface area that you've come in contact with before the casing is put in place is about 30 square meters. If you take that exact same scenario and you put hydraulic fracturing frac with two propped what we call frac wings going off in either direction to a length of about 60 meters, you end up with about 15,000 square meters worth of surface area. If you take that exact same rock and you put a horizontal well through it, and you were to place 15 hydraulic fracturing stimulations on it, all the same length as the one that's on the upper right-hand corner, you now end up with an order of magnitude more surface area. In this case, calculating out somewhere in excess of 200,000 square meters. So it is about surface area. This is what makes these economic, what makes them produce. Unfortunately, Mother Nature hasn't been kind to us. So from one place to another, what would be classified as a shale or an unconventional formation is not the same. They vary in mechanical properties, in reservoir properties, the mineralogy, and so on. There may be quote-unquote technically shales, and even vertically within the same horizon, you end up with variability because, as you remember from one of the slides I showed earlier, the material that we're producing from has been deposited over millions of years, and they've changed in the quality as well. Another thing that varies is the height. So some of the ones that you see listed out on the screen here, namely the Marcellus and the Eagleford and the Barnett, are three of the more successful shale plays that we see in the U.S. today. They are much smaller in scale than some of the others that we see elsewhere in the world. And so it begs the question, well, why is it so successful in the U.S. and in Canada, and we don't see it elsewhere? And the simple reason why is because it's the information that we have. The U.S. has, and Canada as well, has a benefit of having a long history of drilling, and not necessarily into these formations, but in some cases formations that are deeper. So there is a wealth of information, existing wells and so on, where we can tap into that data and basically build reservoir models. So it's that experience that we have based off of previous drilling experiences that we can then tap into building reservoir models that allow us to be more successful. But again, what I'd like you to take from this slide is that variability in the reservoir rock is considerable. So now I'd like to talk a little bit about how we work through the philosophy of going from exploration to appraisal to ultimately into a development phase. So if you take this example, essentially you take seismic data, as is shown on the right-hand side of the screen, and you interpret that information to say, okay, here's the structure that is of interest, and I'm going to do some further exploration into that. And then you map what's on the left side of the screen, the aerial extent of potential play. In this case, we're showing two existing wells, which may have some information telling you that a play of interest exists at about this depth, and you can correlate this back to the seismic information. But this is where the model starts to build. We understand that there's something that may be of geologic interest here and is potentially hydrocarbon bearing. The next thing we do is we start looking at the properties that are driving reservoir quality. So can the reservoir physically deliver the hydrocarbons to a wellbore? And we're looking at things such as the clay content, pore pressure, the stresses in the formation, Young's modulus, Poisson's ratio, natural fractures, and so on. But we look at all this information, including the mineralogy, we start to develop a map saying, okay, here is the high quality reservoir rock. The next thing we do is we start looking at the completion quality. So we start to ask ourselves, can that well physically be stimulated? Can you hydraulically fracture it effectively enough to make it produce? And in this case, we've highlighted that there are some faults that are going through this that would make it difficult in some places to hydraulically frack that portion of the well. And then ultimately we end up with a map that says here's the sweet spot. So even though we started out with this understanding that the aerial extent of the formation technically may be something, that what is the highest quality in order for us to complete is a subset of that. And it's a philosophy that I like to say that in some instances the best well is one that you don't drill at all. So now once you start to build this, you can then develop your completion model. What you see on the screen here is a graphic that comes from one of our hydraulic fracturing models. And it's showing an actual simulation of what a hydraulic fracture would look like for this particular reservoir. So you can see how it is extending out from the blue section, which is the vertical well. And in this case, it is a vertical well. Okay, we haven't drilled a horizontal yet. We're really trying to calibrate and gather information about rock properties and how can the well physically be stimulated, or this formation be physically stimulated. What you see to the right of that is some mineralogy information, pore pressure information, and so on that we've derived from various logs that were run into the well. The next piece over is a production log from that specific well. So it's saying, okay, this is where we physically are producing once we've stimulated it. And then we can go back and we combine that with stress models to be able to go and say, well, this is the fracture geometry look like. And this allows us to essentially continue to calibrate the model and become better at understanding what the extent of a hydraulic frac will look like, both from a vertical perspective and from a horizontal perspective. At that point, and you see the same simulation on the right-hand side, but it's looking at a different perspective, we can then start planning where you're going to land wells. So what you see, the green line running through the black portion of the screen is the horizontal well that's adjacent to that vertical well. Now this doesn't happen on every single well you stimulate. You don't always drill a vertical well adjacent to it, but it's that mechanical information that you get from the modeling that allows you then to transpose that for the horizontal wellbore. And essentially at that point we can go in, we can model what the stimulations will look like throughout that environment. This helps us with things such as how we're going to break up the wellbores, the philosophy on how you'll stimulate, the types of proppants that you'll use, the fracturing fluids and so on. What are the most effective in order to properly stimulate that reservoir rock? And then it's that model that is applied from one horizontal well to the next horizontal well. So now let's talk a little bit about the plays that are happening in the U.S. So you can envision that this map would extend obviously into Canada as well. There are a sizable number of unconventional reservoirs in Canada that are economically viable. But I'm just going to concentrate a little bit about the U.S. experience on this. You see in orange the gas plays, and in blue the oil plays or liquids-rich plays that are existing throughout the U.S. Many of these plays had a life previous to working in the current horizons that they're in today. Some of the newer environments are in the northeastern portion of the U.S., namely the Marcellus and the Utica Shale in Pennsylvania and Ohio, respectively. And it is in those places where the oil and gas industry was largely absent for many decades after the initial shallower plays that were being completed decades ago. And now there's quite a bit of development that's going on in those environments. Additionally, so we see in the U.S. A lot of challenges as far as the different stakeholders that we have to work with. In some places you're working in federal lands where you might have some endangered species or potentially endangered species that people are concerned with. So how you plan the development in that field becomes critically important. In other places, you're working directly adjacent to communities, namely in north of the city of Denver in Colorado. There's a large oil and gas development going on there, and I'll talk a little bit about that here in a moment. As I mentioned earlier, the U.S. is not the only place where there are potential unconventional reservoirs to be developed. We find them all over the world. But again, the level of information that's physically there to allow that development to occur at the same level as what you see in the U.S. Does not exist. So let's just talk a little bit here about global stakeholders. undoubtedly you've heard the term social license to operate. We like to look at this as more of a social contract. A license implies that it's one entity that has the permission to go out and do something, and they're the ones who are ultimately in charge of what the development looks like. We like to look at this as being a partnership amongst many different stakeholders. On the graphic at the top of the screen, you have the communities which we work in and amongst. And their concerns primarily safety, the financial stability, what is this going to do to my community as far as the strain it's going to add to it. In some instances, they don't benefit directly from the oil and gas production. So, you know, their direct benefit from it is implied. You have then going clockwise around this, so you have the consumers. They're looking for, obviously, resources at the lowest possible price. Ideally speaking, it's not happening in their backyard. It's coming from somewhere else. Continuing on around, the environmentalists are looking for, you know, how do you ensure that the air is clean, the water is clean, you know, can we move toward renewable energies? At the bottom of the screen, you have the oil and gas industry, obviously trying to make a profit from drilling and completing and producing hydrocarbons. And today, they're looking at how they can do that with more environmental sensitivity. The next group is the regulators and the legislators. The question becomes, how can we produce this, do it in an affordable manner, but also make sure that we're protecting all the various entities, including the environment. And then last but not least, it's the resource owners themselves. So in the U.S., you have a mix between privately held and federally held resources. And in some instances, you may have folks who own the minerals for the hydrocarbons and a completely different entity that has the water rights. And so those things all play into the complexity. In many instances, they're wanting to be able to produce those, whether it's the hydrocarbons or the water, they're wanting to be able to monetize that. All of them have an equal say, what the development looks like, ideally speaking. So one of the things that we hear quite frequently is that the industry is not well regulated. What this graphic is intended to demonstrate are a snapshot of some of the regulations that exist in oil and gas development in North America. So it's everything from well spacing to well abandonment, site reclamation, the setbacks on the surface from various entities, air quality and emissions, even things like, in some places, around induced seismicity. And of course, as you're probably well aware, North America has, in most jurisdictions, has requirements around chemical disclosure for hydraulic fracturing. But this is just a snapshot. This is not inclusive of all the regulations that we run into in North America. But it's just to give you an idea of some of the ones that are commonly do exist. So we start talking about the basin-based type of regulation. And as an example, I'd like to talk a little bit about Colorado. So Colorado has a long history with oil and gas development. It started out early on in Front Range, Colorado, north of Denver, on some shallower sandstones. What you see, the blue line on this graphic, is the drilling rig count over time. So this is how many rigs are running each month over time. The yellow dots represent key pieces of regulation that were put in place to manage that type of activity. The shaded areas represent different geographic portions of Colorado. So within the same jurisdiction, different geographic environments that we were working in over time. So the first section is north of Denver. These were mostly vertical wells. You can see the rig activity was relatively speaking low, and you see the regulations when they were coming into place. Then in the early 2000s, the gas plays in the western slope of Colorado started taking off. This is a play called the Piceance Basin. Most of these were vertical wells, and you can see how the rig activity spiked at the time, in excess of 100 rigs running per month. And you see that the regulations were coming into place. And then when we get into 2010, activity shifted to the oil-bearing plays on Front Range, Colorado. So back to Front Range, except now we're dealing with mostly horizontal wells in a completely different horizon than the original wells that were drilled out there. And I've highlighted out some of the disclosure, some of the regulations that were put in place to address that type of activity. So there are things such as wellbore spacing, and GWA stands for Greater Wattenberg, fracture disclosure, offset well monitoring. This is from an existing well that may be in a completely different horizon, being able to see whether or not you're physically hydraulically fracturing into that. Spill reporting was updated, wildlife mapping, fugitive methane, water sampling and monitoring, and so on. The point about this is that the regulations are continuing to shift, and they shift according to the types of horizons that are being developed in a geographic area, but also because of the change in activity levels and spacing of wells and so on and so on. But those things are driving ultimately what the regulations look like. Now, the regulations in Colorado, while they may mirror other jurisdictions in the U.S., they have some unique components to it, and others would have some unique components that apply specifically. So in other words, there isn't a standard set of regulations. Here you go. This is what you do, but they're based off of activity and the types of horizons you're working in. So sticking in Front Range, Colorado in this map, you see at the bottom of the screen the city of Denver. The red dots represent wells that exist north of the city of Denver. So there's about 18,000 some odd wells there. Again, some of them are very old wells. When I say old, they might be 25, 30-year-old wells. And some of them are relatively speaking new over the last few years. Now you'll note that there's a hole on the upper portion of this map, and that hole is the city of Greeley, Colorado. Mm-hmm. And that's within the city limits of the city itself, where you have a fairly high density of folks living in and amongst, in the middle of an oil and gas play. That has largely been undeveloped, and in this scenario, operators are looking at using multi-well pads and horizontal drilling to essentially drill underneath the city and be able to produce, staying away from basically the potential of being offset to communities, to homes, to businesses, to schools, and so on. So they're using modern technology essentially to stay out of a certain environment. Shifting to the western slope of Colorado, this is a picture of the Piceance Basin. And this is the Piceance Basin after quite a bit of development. And obviously, this is a completely different type of an environment. Unlike the stuff that's happening today in the Front Range part of Colorado, this is very rural, beautiful landscape and so on, like we see in many parts of the world. And you can make out that there's a road coming up through that creek valley, and you'll see a couple of locations that are apparent there. The vertical relief on this from the creek bottom to the top of the mesas is somewhere around 500 meters in change. And so building roads up to the top of the mesas doesn't make a whole lot of sense. This play, when it was really active, was in the beginning of the last decade, so early 2000s type of time frame. This is an aerial map of that same play. So looking at this little creek valley, you can see where the creek comes in from basically three different directions, and it was on the right fork of this screen where that image that I showed you previously was taken, looking back down toward the middle of the screen. You can make out, if you look carefully, in that valley section, some beige areas which represent the well sites, the pads. So what does this thing look like below the surface? Same perspective. From those pads, basically you're drilling off into different bottom hole locations. Now this horizon is a sandstone, okay? It's a stacked pay. But still the philosophy of onshore pad style drilling was born here, taking essentially the philosophy of what you do in an offshore environment and import it into an onshore environment. What this allows you to do is basically not develop on top of the mesas and work around these environments and work from where the drilling might be easier down at the bottom, but also, you know, access to the land was much easier. This is an image from one of the locations, or a cartoon from one of the locations that shows the different wellbores from a single location going to different bottom hole locations. So you can see that basically the wells are drilled directionally from a common pad and then turned back to the vertical to intersect the target horizon. Now, in order to make this happen, industry had to become somewhat innovative in developing technologies. And one of the things was the ability, since you had multiple wells on the same location, the ability to have the drilling rig move on its own. So after you finish drilling a well, the rig could literally lift itself up and move a few feet, set itself back down, and start drilling again. This is where that type of technology was ultimately derived from. At the same time, when you're drilling wells, you want to start to recoup that investment as soon as possible. So one of the things, another way that the industry changed was to allow hydraulic fracturing to occur at the same time that you're drilling directly on the same location. This image, obviously taken in the wintertime in Colorado, is a hydraulic fracturing crew on location with a drilling rig. What's difficult to make out on this image are some of the details that occurred in order to make this happen, which included a blast wall that exists below the rig to prevent that if there was ever an accident on the hydraulic fracturing side, that the rig would be protected from it. On this location as well, there are wells that are physically producing at the same time. So essentially, you end up having what we call simultaneous operations occurring on location. But this required management and change. It required the companies that are doing these types of things to develop new processes and procedures to work on that in that unique type of an environment. Finally, this is what the end result looks like. In this particular case, and this is an extreme, is 52 wells on a 3-acre location, all going to different bottom hole locations. There are some inherent benefits of doing this as well from a production perspective, that all the production is being gathered to one location, and from there it's being managed as opposed to it being individual locations, and then you're collecting the gas or the water that's being produced and having to take it to another location. Now I'd like to talk a little bit about the learning curve, okay, and this is on the drilling perspective. We see this repeated in every basin that we work in. The first well that's drilled is the least efficient well. It's the one that's drilled the slowest. There may be things such as data that you have to collect, and so you're drilling much more slowly. But you're also looking at the combinations of drilling fluids and bits and the right equipment in order to become very efficient at drilling. What this graphic shows, the blue line, is the days from spud, which is the starting of drilling, to rig release. So when the drilling rig is done, hydraulic fracturing hasn't occurred yet. So we're looking specifically at that portion of the operation, which is drilling the well. So the very first well that was drilled in this particular horizon, which is in the beginning of 2010, the bars represent the number of wells that were drilled each and every month. That very first well took in excess of 3 weeks. Today they're drilling the same wells in less than 1 week. So it's that learning curve was significant. We see this again in all plays. And one of the key advantages of climbing up this learning curve, the experience that's under your belt, but also the fact that when you're more efficient, ultimately it means that there's less amount of time that you're impacting surface entities, stakeholders that may have some either live adjacent to wells or maybe it's wildlife in the area and so on. In other words, you get the wells drilled and completed quicker. The next piece is the well integrity. Obviously the most important component of a well is the construction and the cementing of that well and preventing contamination into aquifers and so on and so on. Cementing of wells is not like building a sidewalk. The technologies that are employed are different. You may have the same basic product, Portland cement, but what we're doing is we're creating a barrier to prevent fluids and hydrocarbons and so on from migrating to other horizons. Now, the technologies that are derived here are pretty significant and impressive. We have today technologies that allow the cement system, after it's been set, to essentially reheal when it comes in contact with hydrocarbons. So hydrocarbons, it senses hydrocarbons and it can fix itself and shut itself off. We have technologies that allow us to work in places where you have corrosive fluids. We have technologies which allow us to work where you're going to have repeated temperature changes and stresses that are associated with hydraulic fracturing. But the engineering of those technologies, the design, depends upon the environment you're working in and what you plan ultimately to do that well. In addition to the physical cementing technologies, you also have things on how you design the cement jobs. We utilize software to basically model the cementing, because one of the critical components of cementing is the removal of the drilling fluids. Also making sure that the casing that is put in the well is properly centralized. So when you're displacing drilling fluids out of the well bore, the flow on the annulus will allow essentially the washing of the drilling fluid back out and provide a better area for cement to bond with both the formation and the casing. But it's that type of knowledge, the deviation of the wells and so on. Do I have any losses that may occur in the formations? It's those things that drive the cement design. And you can get to a point where you understand that in a particular field, I'm dealing with this temperature range, I'm dealing with this type of corrosive fluids, and so on. And you get into the generalized design of what you're planning on doing. But then on each well, you will go and run a specific lab test to determine that the cement is going to perform correctly. Will it mix correctly, and so on. So we collect samples after it's been blended, the actual sample that's going out to location, and then it's tested to make sure that it's going to perform correctly. And then last but not least, the equipment that we use and the expertise that our folks have to allow the cementing process to occur. So on location, the amount of energy that's put into mixing the cement is critical. So the equipment is specifically designed to allow us to mix cement on the fly and be able to get to the right density and to be able to have the cement perform in the same way that the lab results showed that it was going to perform. So let's shift gear and talk a little bit about water. This is a recently updated table showing water per well for various U.S. basins. And you can see, I mean, it does vary. We have some plays like the Haynesville, which use a considerable amount of water. And also what I'm showing on there is the second column from the right is the amount of water that's recycled on a per well basis. Now this varies from play to play. We see in the northeast portion of the U.S., Marcellus and Utica, the highest level of water recycling. We don't see it in other places, and in some instances it's because you either don't have a lot of water available to recycle, to reuse, or you're getting water from somewhere else, maybe from a landowner, a rancher who is providing you water. But that's just to get you an idea of what we're talking about on an average basis, how much water is utilized. One of the key things that we saw as an opportunity, because we don't always have flow back water from previously fracked wells to allow us to stimulate the next well, is could we use the produced water that's coming from a given field to act as our source. As I mentioned to you before about the amount of money that we spend on research and engineering, a group based out of the U.S., which is what we call our client support lab, decided to take this project on themselves. So it fell out of the normal research and engineering processes we have within Schlumberger, but they were trying to tackle the idea of can you frack with produced water. And their goal was to develop a technology that allowed you to use produced water without treating it. So you can envision that when you treat water and you're trying to get the salts and other things that are out, you're creating a residual waste stream that ultimately has to then be disposed of at some sort of hazardous waste facility. The goal was, can we just use produced water the way it is? So they developed a technology that allowed us to work, and you can see for this example here at the top of the screen, this is the salts that we had in this particular sample. And you go from the water that's on the right, which is orange in color because of the iron content, to basically the fluid that's on the right-hand side that has some viscosity and allows the proper transportation of proppant into the ground. So we were able to achieve the properties that we want and being able to use 100% produced water without having to do anything with it. So we thought, look, this is great. And a lot of folks are going to be wanting to use this. Unfortunately, going back to the regulations, what we found out was that the regulations that had already existed in many jurisdictions throughout the U.S. do not allow the accumulation of produced water. So produced water is treated as oil field waste and has to be disposed of expeditiously. So even though that technology exists, the regulation did not reflect the ability to, that technology was continuing to change. And that's something that today the regulators understand, and they're actively working on how to achieve that balance where somebody is not just accumulating produced water, not disposing of it, but that you're going to be using it for that next phase. On a related note, that type of philosophy allows us to do things like reduce emissions. So I've taken the typical amount of water that is used in a U.S. shale, and I said, okay, if you were going to have to truck all that water to a location, plus the proppant and everything else, how much equipment are we talking about? How many truckloads of water do you require? And then if you have existing production already within a play, and you're having to get that production off and send it to some underground injection control or other way of disposing of it, you have trucks going in the exact opposite direction and carrying things off location. And technology has continued to evolve from where it stood, where that was the way you would do it, to where today you can go out there and use various technologies to reduce the water requirements, number one. But then number two, be able to use water that already exists within the basin to stimulate the well, or stimulate the wells. And so the right-hand side of the screen then shows what that would look like. And because of that simple thing of being able to plan and how you use equipment and water that exists within the play and so on, that allows you, in this case, as an example, to reduce truck traffic by over half and to reduce the corresponding emissions significantly because you don't have all that truck traffic in the field. Another practice that's happening commonly in large-scale development in the U.S. today is that where you can, you'll develop some sort of water system within the play that allows water to be piped to locations. So instead of having to truck it, you can move it across the surface in pipes to get it to location, which further reduces the emissions. So by using those technologies and those types of philosophies, you're able to take the emissions significantly down from where you would have been if you did absolutely nothing from a logistics perspective. So let's talk a little bit about chemical disclosure. So hydraulic fracturing chemical disclosure started in the state of Wyoming in the U.S. in 2010. That was the very first jurisdiction to have a regulation requiring such. At about the same time, the oil and gas industry was working with the Groundwater Protection Council and the Interstate Oil and Gas Compact Commission to develop a chemical disclosure registry, which today you probably know as Frac Focus. That process started in the beginning of 2011. It was voluntary at first, so industry was essentially voluntarily, no jurisdiction was requiring yet, disclosing to this database. It was later in the year that we started seeing the first of the jurisdictions that were requiring disclosure, and they were basically pointing to Frac Focus. And today, Frac Focus covers essentially all the jurisdictions where we're fracking. So the shaded area of this graph shows the percentage of the global fracturing market that is under chemical disclosure requirements. So essentially, anywhere that we're hydraulically fracturing globally today is under some sort of disclosure requirement. Again, some of these predated Frac Focus, and as such, they don't reflect it. They don't reflect the requirements that are in Frac Focus. But most of the operators, in my experience, that are working where there are requirements to disclose are also applying those same disclosure standards to jurisdictions where they're not required to do so. Now, you will note that there's a couple of places there that are outside of the U.S. So in beginning of 2012, British Columbia, Canada became the first province to require it. And then in mid-year 2012, Western Australia required chemical disclosure, but not only for hydraulic fracturing, but also for drilling fluids and cementing as well. Today, Frac Focus allows two different options for disclosure. The process that we use is what we call a system-style disclosure. Essentially, we can disclose 100% with little to no reference for proprietary chemistry because we decouple the chemical constituents from their parent products. So in other words, if you have something that has a surfactant and a breaker and other products in it, and those individual products may be made up of different chemical constituents, by going out there and saying everything that went through the wellhead and decoupling it from the parent products, it makes it very difficult for somebody to go out there and reverse engineer. Now, if you look at when chemical disclosure first was required in the U.S., we've been applying the same process since 2010, and that process, to date, we have not found a single instance where somebody has gone out and reverse engineered what we've disclosed. So last slide, and I'm going to turn it over to Paul. This is the transition to Northern Territory. In 2011, we had a customer that was proposing to do some work in Northern Territory, and they asked us for a chemical disclosure. We happily provided them chemical disclosure, full disclosure, so they could do their planning. This is, again, without a requirement for disclosure to happen. The philosophy is simply that if we can disclose that fluid in a jurisdiction that requires it, we can surely disclose it in a jurisdiction that doesn't require it. So we supplied it to a customer so they could then do their planning. So with that, I'll go ahead and turn it over to Paul.
Thank you very
Got
much.
10 minutes left, gentlemen.
No problem. I'll be very brief
No,
here.
sorry.
Get this.
Might be even briefer.
Get this happening again. Duplicate. Yeah, this laptop's fun.
Apparently.
Okay, so changing gears completely from Joe's experience in North America, in Colorado in particular, and I'd just like to briefly run through Schlumberger's experience in the Northern Territory. So, as you know, we're a service provider. We break our business up into different pieces. We have something called Schlumberger Land Rigs, formerly known as Saxon, and we also provide services such as cementing, fracturing, wireline, and other elements to the work that happens in the Northern Territory. So the Northern Territory campaign is primarily, it's a very significant logistics exercise, getting all the people and equipment to the field location. And we did this via charter flights in and out of daily waters, Elliott, ex-Darwin, weekly crew changes, ad hoc drive in and drive out ex-Darwin for VIP visits or specialist visits and buses. So the rig activity was typically 50 person for the drilling project. Services and frac and other was an additional 70 people that were mobilised, and we had no HSE or environmental incidents for the duration of the campaign. So just to give you a bit of a breakdown of the inputs into the local workforce and economy. So the local supplier spends in 2015 was just over 240k, and in 2016 was just under $500,000. So the key suppliers, local suppliers, was in Katherine, engineering services, recycling services, lots of accommodation at the Lima Hotel, the famous Pink Panther, and at the Daily Waters Highway Inn, Indigenous Beverages Australia, and the Northern Territory government, and Viola Environmental Services out of Katherine. So this is just for a small, limited campaign, but it's still a significant spend that gets contributed to the local economy. An aerial photograph of what our drilling operation looked like with Rig 185 on the Amungi campaign. You can see that the ponds in the background there for the conventional and underbalanced drilling. This was what we would regard as a relatively compact footprint. Now this is not what a development footprint would look like. This is the exploration phase. There's more equipment and associated services required, but you get an idea of the impact. Approximately 200 by 100 metre footprint. So something that was very meaningful for the team on site was organised by Origin with the local traditional owners, was a welcome to country ceremony, and if you talk to anyone involved in this campaign, this is something they will remember very, very distinctly. And as a company, I'd just like to highlight some of the things that we are doing in Australia in terms of engaging with the traditional owners. A reconciliation action plan has been conditionally endorsed as of April of this year. We're working with the Clontarf Aboriginal College University in Western Australia. We're providing internships, visits for students to our facilities. We do defensive driving training and practicing for interviews, interfacing with the corporate world. Closer to home for me, in Roma Technical College in Queensland, we've had a couple of interns of Indigenous students in our Roma base in the wireline facility in Roma. We have apprenticeships. There's one ongoing now with a mechanical apprentice who's working in the hydraulic maintenance of our tools, and the local community has been providing cultural awareness sessions. About 14% of our local spend, this is with local suppliers, is going to Indigenous suppliers. We started this initiative in 2016, and we've been assisting local suppliers with the onboarding process with a big company like Schlumberger, how to navigate our procurement processes and be part of our supply chain. Something I just did myself recently, I'm on the executive committee for the Cooper Eromanga Basin Aboriginal community, and we did an on-site session at Lake Killalpanina, just off the Birdsfield track, and we held the annual conference there. I brought some of Schlumberger's management, my family, and we got to interface with the traditional owners, including the dairy people, and understand their connection to the land and how they can participate in our business, and we anticipate doing much more of this in the Northern Territory. Just another couple of photos. Now we're moving on to what the frac lease looked like during the drilling phase with the rig on site, and this is our people on site with on rig 185. Something we did with the regulator and the NT government was that we created a model so that we could illustrate to the regulator there what the cementing process like, what the casing design looked like, so he could help educate his employees and workforce as to what we're actually doing. This was constructed by the Schlumberger Land Rigs team in order to foster understanding of what we're actually doing and how this regulation applies to us. Now moving on to the frac side, as again we treat that as a distinct operation. The rig had demobilised. Here's a photograph showing what the frac spread looked like on site. We spent about $345,000 on waste and recycling out of Darwin using Cleanaway, again the Highway Inn and Indigenous Beverages of Australia. It was Origin's first fracturing operations in remote Northern Territory. One horizontal exploration well was drilled in 2015 and re-entered towards the end of last year with 11 frac stages, the shale target, high pressure treatments, 2 stages per day achieved, and we had 0 safety incidents with a total of over 18,000 man hours. 382,000 kilometres driven with no vehicle incidents and no lost time injuries for this operation. So a key contributor to the success of this campaign was the engagement with the local suppliers, which is the Toll NT team based out of Darwin. They also provided Indigenous site coordinators that worked with the water and sludge hauling teams. Toll did the vast majority of the kilometres driven for us, over 200,000 kilometres from Toll. So I'd like to just quickly share with you, this is the rig superintendent for Rig 185. He is a local Territorian boy. He's got a farm in the Finnis River. He's a sole trader, and it's cattle is his business. He's Adelaide based at the moment. He's looking after the rig that's working for Beach Energy in the Cooper Basin. He started with Schlumberger out of Darwin. He considers Darwin home. He's had a career spanning Venezuela, Bolivia and Colombia before returning to Australia for the last 7 years. He's a keen Northern Territorian, and I think you may have met him. I brought him to the Daily Waters engagement session, and we sat at a table with the pastoral community, and he very much fits in with that pastoral community. So I just wanted to highlight from my perspective the engagement of local people and what that means for a career. I myself started in Darwin in the Northern Territory in 1991 and spent about 5 years working the Territory, grew greatly attached to it, and then have been out of Australia for 20 years and have now returned back to work in Australia. So I just wanted to pass on our much lower key and short experience in the Northern Territory that we've had so far and what it potentially means for us. And that is it from us.
Thank you. Thank you very much, gentlemen. I have a list of questions, but I think I will actually open it up to the panel first to ask questions before I dive in, because I'm quite sure that probably they'll all get answered during the course of the questions of others. Thank you. Yes, who'd like to go first? We'll start and work our way down. How's that? Dr. Jones.
Yeah, Joe, this is probably a question to you. One of the things that's greatly concerning us in our constituency is well integrity, and particularly well integrity post-decommissioning. Now, we've seen lots of stats coming from the US, which is arguing that things haven't improved with technology. The well integrity is still as poor as it ever was. And most of these things seem to use methane as an indicator of issues rather than actual water contamination. Could you comment on some of those things?
So you're talking about sustained casing pressure and so on?
Certainly during operating, yes.
Yeah. So first of all, sustained casing pressure occurs on the annulus of the production casing. Remember that there are several strings, as the graphic that Paul showed. The model is intended to show that, adjacent to the aquifer, you have cement and casing, and then you have other cement and casing strings that are inside. So the sustained casing pressures that we do see are typically at the annulus of the production casing. And they don't have a sustained flow, though. So in other words, they blow down, and you have some migration of methane to the surface in some instances. It's one of the reasons why we've worked and developed technologies to allow for the cement essentially to shut off when it sees any hydrocarbons coming through the matrix of the cement itself. They can basically reheal itself. I can't answer the question about, that the technology has not improved it, because I would generally say that it has. Because we have seen repeated technologies that have worked toward these various issues, but I'm not familiar with any widespread that says that this is always has been an issue and will continue to be an issue. But generally speaking, we've seen improvement in cementing quality in the States. And remember the other thing is that the application of cement depends upon the environment you're working in. So what you're going to do is be dependent specifically to the types of fluids you're coming in contact with.
But certainly this issue of well integrity and statistics is a recurring theme that keeps getting thrown to us, and we're not experts in petroleum reservoir technology or drilling, and so we would like some kind of definitive answer as to yay or nay. Is it getting better, or is it the same as it always was? And what does methane detect mean? Does it mean an issue of human health or environmental harm potential, or is it just a case of this is something that's used as an indicator, but it's not necessarily a good indicator of that?
So I can't answer about the human health effects and so on from it. That is it systematic problem that is ultimately leading to health effects. I don't have that type of expertise. I will point out that you're talking about 30 some odd thousand wells that are drilled in the U.S. on an annual basis, and of those, I think that we're talking about a relatively speaking small fraction of these that we're seeing these types of problems that are being pointed to. So I wouldn't say that it's an example of happening on every single well. If you drill a well, you're going to have this issue.
We appreciate this, but we've seen some statistics, for example, from King & King, which is an often quoted. King & King that produced a paper, I think, in about 2013, which suggested that the issue of total wellbore failure was about 0.004%. Yet other protagonists are coming out saying that the issue could be up as high as 6% or even higher. So are we comparing apples and apples? I think that's the key number of the question.
So I can tell you that the proper use, I feel firmly on this, that the proper use of technology, you can achieve the goals of properly sealing off the formations, and that the technology allows you to work in an environment where you're constantly stressing the casing, changing the temperature, and so on and so on. So again, it's the proper use of that technology that allows you to achieve that goal. Can I say that we're always seeing that proper application? There are going to be instances where folks haven't applied these things correctly. So I think it is a matter of understanding the environment you're working in and saying, what tools do I need to properly do it? I think it is achievable. I think it's achieved more often than it is not.
Just I guess a follow-up question on that is post decommissioning. We have the perception from the community that at the end of a well's life, that it's something like a genie in a bottle, that unless it's really plugged up really well, that you're going to pop the cork and things are going to come up the wellbore. Is that the case, or have these systems been so depressurised that that's not likely to be an issue?
Well, so I think you do have the advantage that you've depleted the target reservoirs, and so when you're plugging the well, you're no longer in a commercial state, that you have the benefit that it's, you don't have the same amount of pressure being exerted in the overall system. I've heard the question before about, is there, 100 years from now, what does a well look like? There aren't a lot of examples of that. In plain and simple, there are not a lot of examples for us to rely on. I can tell you that the ability to go out there and understand if you have a problem in a string of casing. In other words, looking at corrosion in casing, or does a cement exist behind casing, and so on. Those technologies exist. They're tried and true, and that the application of those technologies will allow you to understand what you're dealing with. The cement systems themselves, if you end up, like, let's just say what we call a primary cement job is the first application of cement into that well when you're trying to cement the casing. A remedial cement job is when you're going in and fixing a problem. Okay, maybe you have some sort of place where the casing was laid up close to the formation, and you have a channel there. There are cement systems that are specifically designed to allow you to get it to those places. So the processes of going in there, perforating the casing, and then doing what's called a squeeze job to squeeze that off exist. And so, it is that type of application that allows you to achieve the goals you're intending. I don't know of any examples, I cannot think of a single example at this point of where somebody said, here's an old well, we've had to go back in, or we're going to have to go and fix it. It's, it's been plugged for some time. So I don't know of any examples like that. But in theory, if you run across that, I think you can go back in and fix that problem, so it doesn't become, a perpetual issue.
Yes.
Yeah, thank you for the information you've provided on the disclosure of fluids, chemicals used in the process. Hopefully we'll have access to the slides so that that information can be captured. I have a two-pronged question, really. The first relates, in some of the submissions we've had allegations that depleted uranium is used in some of the fracking processes. If this is the case, what is the function of that depleted uranium? How is it used, and how important is it to the process? And the second part of my question is that there's also been an allegation that Schlumberger was fined for having some of its workforce in Queensland exposed to radioactive materials. If that is true, can you explain the circumstances under which that actually happened?
Yeah, so I'm unaware of the use of depleted uranium in fluids. I've not heard that before. And, so I can't really answer that question. The second piece of it, if you don't mind repeating, what was the case you were referring
And I
to?
can,
Well,
I can take that one.
Paul can
Okay.
take it.
Yeah, and look, it is a legal matter. I would prefer to get the appropriate legal representation. I'm happy to connect you with them, and you can have that discussion.
You're not able to describe the circumstances under which it may have occurred?
Dealt with, heard.
It's been dealt with as and heard, and I'm not an authorised spokesperson to handle that. I'd be happy to connect you with our legal counsel who can go through those circumstances with you.
Wouldn't mind, that would be
Yeah, no, happy to do that, and I predicted that question, and I have this answer ready, and happy to connect you with that individual, if you don't mind.
Okay.
Yeah.
Yes, no, that's right.
I had a question on the well integrity. You mentioned proper use of technology.
Mm-hmm.
Everything was A-OK. How do you describe proper use?
Yeah.
And how would you expect it to be? What are the sort of guidelines? Do you, around the world, what do the various jurisdictions have to ensure that, one, we know what proper technology is, the best available, and that it's actually being regulated?
Yeah. So, what typically happens when you're developing a play is that you look and you say, what other plays around the world are analogous to this? Okay, and then you may start from that point. You say, well, this particular play in Northern Territory is similar, let's just say, as an example, the Marcellus, okay? And you start saying that from a reservoir perspective. I mean, that's really where the relationship stops. When you get into a specific field, you do have to understand things such as, especially with cementing, temperature anomalies.
Yep.
Okay. You have to understand, do I have any corrosive fluids that are native to the rock, to the formations, whether it's the producing formation or any other formation that you've intersected? What do I have? Am I going to encounter anything that's ultimately going to either have an issue with the cement, or I'm going to have an issue with the casing itself? In other words, does that fluid get to the casing and start corroding
Sorry to
the casing?
interrupt.
Yes, sir.
Yeah, that's. I understand all of that, the site-specific situation, but I'm trying to work out how then the knowledge that exists within your companies and like companies, number one, the regulators know about it and can act on it, because otherwise I got the juxtaposition between what might be the right technology and what's put in guidelines, regulations or whatever, and then the community feels happy that the regulator
Right.
is on top of things. That's broadly where
Yeah.
I'm going.
Well, remember that these wells are intended to produce for decades. So, I
Sure.
mean, the operators of the wells, their goal is to get that piece of this. The time that you have to get the cementing done right is the very first time around. So I was getting a little bit of a long-winded answer to your question. I don't believe that, my experience is, I don't believe that the regulations will describe what the cement systems need to look at, but
Right.
it's the experience that you have at the field about the conditions I'm working in, okay? And then deciding upon which, cement systems and so on make the most sense to use, and even again, our models, allow us. We use these things as best practice. I mean, there are requirements on testing. Some of those requirements are our own testing. Some of them may be jurisdictional, but we have certain protocols on how you apply these things to the cementing design process. But then once you've applied all these things, it's a matter of having all the right experienced people and the right equipment to physically get that place. But the decision ends up being, like with folks like Daniel, based upon what your experience is in the field, that particular field, and then working through the depth of knowledge that he has, but also other folks within the company has. So one of the things that Schlumberger prides upon itself is that we work all over the world. We work on many, many wells, and we have some internal communication systems that allow our technical folks to ask these questions of experts throughout the company. So essentially, you're virtually tapping into experience from all around the world. If you have something that's unique that's occurring, you can go and ask the question, has anybody else
Yep,
dealt with this
sure,
type of thing?
sure.
So now, again, once you get to that point where you've designed this, cement, treatment, then it's going to vary from well to well to well based upon the unique circumstances
Yep.
that you're running into. But it's all these things. I mean, cementing isn't just as simple as going out there and mixing cement with water and pumping it. There's,
No.
There's a lot.
I understand all of that. I'm just the background to my question is we have had submissions and community consultations, and I can tell you the great majority of people out there, and the unwashed, if you like, don't trust companies and they don't
Right.
trust governments. So we're very keen to think about what are the processes that we can put in place that might assist that confidence.
Yeah.
That's all. So
Yeah.
let's leave it
Okay.
at that. I think
Fair enough.
that's fine. Can I just ask you another question?
Yes,
that-
sir.
and it has to do with operations under difficult conditions. You showed the one in Colorado, snow in the winter. We've got the similar, if you like, but different, wet season, and we've been putting it to a number of organisations, the Origin and Santos and so forth. What about not necessarily operations, but no hydraulic fracking during the wet season? Because, transport, you brought up the whole transport situation. Most of those cases, I suspect, were paved roads. We're going to have one
Right,
made paved
absolutely.
road, and then the rest of it, and the pastoralists know that they essentially do nothing during the wet season.
Right.
So what's the story there? Do you think?
Yeah, so
No operation?
Well, so we run into that, right? I mean, we run into this in places like Canada when they have that transition from the winter time to the spring, the breakup.
Oh, yeah, yep.
Okay. And yes, operations stop at that point, and mostly it's because of the impact it has on roads and so on. Now, we have run into places where we know that we are going to need a lot of sand, for hydraulic fracturing
okay.
operations.
Yeah,
and
yeah,
this is in the U.S., and this is, paved roads and so on. But again, driving down a winter road can be, when you're sharing it with school buses and other things, you have to think about these things. So what we did to solve that particular issue is that logistically we built a facility that allows us to go and get the resources we need closer to the field and then be able to transport them a shorter distance instead of utilizing the network of roads. So it's those logistics. I mean,
Yep.
it's not just what you're physically doing on location, but I mean, a lot of this is around logistics, the transporting of resources and so on to location. So that planning is important. But the other thing is that we're continually striving to how we can do these types of things. How can we achieve these things with less resources? I mean, that is our goal. As I mentioned to you earlier about the importance of surface contact with the formation.
Yep.
Okay, that's what drives the reservoir performance. The physical getting creating that hydraulic fracture and so on, we've continued to look at technologies that allow us to do it more efficiently with less water, less proppant. And so the application of those technologies, is a potential in some types of environments. But I think that ultimately, if you're looking at some concern with, the roads, or, what little roads there are in those areas, or the potential impact to the environment, you may end up having to consider,
Yeah.
doing something like that.
No operations.
Yeah.
Yep. Thank
If
you.
I can add to that, if you wouldn't mind,
Yeah,
from
sure.
personal experiences, there is obviously extensive flooding in the Northern Territory that Joe, it's incredible actually how much of that country does
Indeed.
flood. We have similar experiences in Queensland during the wet season there, and you can plan your activities to constrain it to areas of high ground.
Sure.
You can stockpile. It really becomes a logistics optimisation exercise. We work in many jurisdictions around the world and can manage all sorts of logistical constraints. It's a matter of whether it's a cost-effective way to proceed. This would really be an operator decision. that we could fit into. They may hand some of it to us. Schlumberger, see if you can plan about putting a rig on this high ground for 3 or 4 months while it's flooding, and what can we achieve in that period of time.
Yeah, it's the planning,
Yeah.
as you were saying.
Yeah.
Just one more, if I may.
Yep.
It has to do with the fact where we are at the moment in the NT. You know, there's a couple of wells and that's it. And so the question is around strategic rollout. Have you any experience of, you understand what I'm getting at, that it is very, the hypothesis would be the rollout of the industry, the unconventional, in say in the Beetaloo, is very well controlled by an independent authority. Are there any other examples that you know of around the world where that has occurred, or is it? I mean, you know, we get the comments all the time about the uncontrolled development in Queensland, et cetera, and I don't know, I don't have experience of Canada and the States, but you get the same sorts of situations.
Yeah, so, you know, I think that there's some natural constraints that occur specifically about where you are in the development process today, which you're not in development.
Yeah, exactly.
You're in exploration and maybe into an appraisal type phase. And so what I try to articulate in some of the slides here was that on the field development perspective, you know, it starts out slowly because you have to build that model. And, you know, before you can get to where you're doing large-scale development with a lot of wells, you have to understand what you have. So I think that there is a natural constraint. I can't think of any specific examples anywhere where that's happening, you know, by design, as opposed to just happening from a natural perspective.
The knowledge build-up.
Right, it's a knowledge build-up that takes it slow. Okay. But again, remember that it is that in our perspective, most of our customers' perspectives, it is about being efficient. Okay, so you know you'll look at building pads where you can for multiple wells and drill off that type of planned scenario. So I think many of the images that folks are leaning upon and saying the uncontrolled growth ends up being some of the vertical wells and so on that occurred, you know, in the last generation of oil and gas development in the U.S. I keep on seeing those pictures popping up as examples, and they're not the contemporary of what's happening today.
Yep, thank you.
And maybe just following on from some of the questions that Barry then asked. I mean, we know that there are problems in Texas. We know that there are problems in Queensland. We know this because, you know, we know that arguably that social license has been lost, or social contract, to use your words, in Australia. We have a moratorium now in place in WA. We have a moratorium in New South Wales, and we know that there's gas in both those jurisdictions. It's banned in Victoria, query how much gas there is, banned in Tasmania, moratorium in the Northern Territory. So there have been problems. I mean, that's what spawned really organisations like Lock the Gate and others. What went wrong in those jurisdictions? What you know, why is your industry now very much on the back foot?
So two things. My personal experience is, you know, what keeps me up at night is not what we do, it's what people think we do. Okay, that's the big concern that I have. And the other half of this is that, generally speaking, engineers do a very poor job of communicating with the general public. So I think that our ability to go out there and communicate what's happening, and then, you know, maybe there's an inherent mistrust for companies and so on. I think that is out. You know, we're being outpaced by folks who don't want to see development versus folks who understand clearly what we're doing. I'm a firm believer that knowledge is the power behind doing these things correctly, and that if you understand these things, you can engineer things correctly. So I think that to answer your question, the big issue, I think, is taking some examples and using them out of context and saying this is a systematic type of issue that you're having in a that's going to follow you to Northern Territory or anywhere else.
Well, it's more than that, though, isn't it? I mean, there's truly, you know, to sort of overly simplify this, there is no smoke without fire. We know that there are environmental and social problems that exist in Texas, that existed in Queensland. I'm not looking for an answer that's prospective. I mean, I appreciate that technology has changed. I appreciate that the way things are done now, even from a social perspective, have changed. But what happened, putting your glasses on and looking back, why did things go wrong? And they did go wrong.
Yeah, I mean, again, I'm a believer. The things that I've been involved in, the things that I've seen, have been primarily a miscommunication of misrepresentation of what's going on. I think that there are quite a few studies out there, and I look at this from that if you really want to look for something that says that something's not working, you will find something to support your belief, and then that's what you'll use as a banner. I don't believe that we have a systematic issue in the industry that is going to again say that just because you're doing unconventional development onshore in a given area, you're going to run into the same problems you ran into Texas or in Queensland or any other place.
I'm not asking you that. I'm asking you what. I guess I'm asking you what. First of all, do you accept that there were problems in Texas and Queensland, just to pick two jurisdictions?
But I'm not sure which problems you're referring to.
Well, in Texas,
if you could be more specific, I'm sorry.
There's instances of sort of, aquifer contamination, health problems. I think it's fair to say in Queensland, as a result of bad practices between gas companies and landholders, there was a lot of stress and anxiety created in those communities. So we know that things went wrong, and I guess I want to know why you think that is. Was it a failure of regulation? Or were the regulations there and they weren't followed? Or were they just, what are your learnings, I guess?
Yeah, what's changing, what I see happening with the E&P industry in the U.S. is that they're changing how they're communicating, okay? The cases I think that you're referring to, the groundwater contamination, health effects associated with oil and gas, are, that you may have a study that says that this has happened, and you'll have other studies that say, no, this hasn't happened. And so I keep on seeing these conflicts as far as, what the real results are of these various studies. But, I see that, first of all, I think our industry is extremely innovative. We continue to share best practices, and some of the things that you're hearing as far as plans by Origin and others are derived on some of the better things that have happened out of North America. So, how you drill, how you complete pads, the proper use of fluids, chemical disclosure, all those various things. But so I don't see that as being a problem. Now, I will say that in the U.S., many of the regulators, they work together from a standpoint of helping each other understand what the regulations look like. There is an effort that exists through the Interstate Oil and Gas Compact Commission called Stronger. I don't remember exactly what the acronym stands for, but basically it's essentially a peer review of the state regulations. So if you're a head regulator in a certain jurisdiction, you can say, I'd like to sponsor, to have a review of the regulations. And in the other jurisdictions will basically, come in and they'll look at what's on the books, and they'll say, here are the places where you have an opportunity for improvement. And so you do see that there is somewhat of a march, that commonality between jurisdictions based off of those types of things, and so they do listen to what's happening in other places, in other states. But again, to go back to what you mentioned before, I would say that the studies that you're referring to about groundwater contamination and so on, I have seen studies have also said, no, that's not because of this particular thing. So you didn't do this, right? You can't say that it was definitely that happening. Industry wants to continue to have that social contract, obviously, the ability to go out and have that trust. It is somewhat of an uphill battle, right? To gain that trust. And again, that's why we see that many companies have these social programs and these programs to try to communicate what they're doing and what their plans and participating with the communities and so on and various things, because they're trying to build the trust, have open dialogue, open lines of communication, and so on.
All right. Thank you. again, perhaps you can just, give us on the regulation theme, what in your experiences would be some of the toughest jurisdictions in either, both in North America and in Australia
I'm
in
sorry,
terms
the
of regulation?
toughest?
Toughest, the most onerous, most inefficient or expensive, perhaps, to boil it down,
Yeah.
regulations to comply with, first in North America and then in Australia.
Yeah, I mean, so I can't, I mean, that's a tough question. What is the toughest one?
What is the most difficult?
Well, so, you know, I live in
As I said,
Colorado.
expensive.
I'm more intimate with what happens there from a regulatory perspective. And remember, I'm speaking from a service company perspective. It's
Sure.
My personal experience with this. I see that, like, Colorado has been very progressive. And they've come up with things like, you know, fugitive methane regulations and so on ahead of others. And so, but many of these things, industry voluntarily worked with the regulators to develop. To, you know, here's a problem that we're all trying to address. So they're coming up with something that makes sense. I can't say for a fact that it's more onerous because, you know, we're not the entities that ultimately are living up to those
No, it's fair
specific
enough, that's fair enough.
regulations.
Thank you. Yes, Dr. Beck.
Thank you. I just want to continue the theme of abandoned wells.
Okay.
I've got two questions, one on abandoned wells and another one on rigs. In terms of abandoned wells, I've recently read a paper in the United Kingdom, from the United Kingdom, reporting on some 190 odd wells that had been decommissioned, so removal of infrastructure and burial. And they measured the methane emissions at the surface, so in the soil, and there was a very high percentage of leakage wells. And it wasn't a few percent, it was tens of percent, could be 40%, I just can't recall the figure. And there was a distribution, obviously, of the amount of leakage that was going on. And they found that leakage occurred fairly early in the life, and it wasn't a function of the age of the well, it was more that they happened fairly early. If they're going to leak, they leaked, and they leaked reasonably early in the life. So I'm coming at this from a perspective of social licence to operate.
Mm-hmm.
There's evidence that there are problems, and these are not abandoned wells, these are decommissioned wells according to UK regulations, so rigorous decommissioning requirements. We've got evidence of leakage, and they were speculating as to why they were leaking. Cement was clearly the one. They were speculating that it could be leakage from gas seams higher up rather than low down. And they were speculating as to how to try to prevent this because at the moment we're talking about a social licence to operate. We have evidence that there are significant leakage problems and we can't dismiss that. So I'm looking to get some suggested solutions how we can overcome this problem so we can try to alleviate community concerns. Now, interestingly, in the paper they did suggest something that you had noted was that use of, but in a different context, you were talking about remediation of wells and perforating the casing and squeezing the cement. Well, they were, I think, suggesting using that as a more routine procedure to try to overcome these fairly high percentage of leakage. So I'm looking for suggestions as to how we can get procedures in place because current procedures clearly on the evidence are not working and what we can do to try to develop a social licence to operate.
Yeah.
Because if we don't do that, there are going to be problems.
Yeah. So I'm not familiar with the case you're talking
No.
about, but I'm assuming these are in the UK.
It's in the open literature, yeah.
And you know, one of the things, I mean, Schlumberger, just to give you a little bit of an idea of where we sit from a regulatory perspective, we don't lobby, we're apolitical and so on. So, you know, I'm not going to go out there and tell you that this is the regulation you need to put in place. Again, I know the common theme that you're going to hear from me is that the proper use of technology, I think, is going to be the type of thing that enables us to reduce the likelihood of these things happening in the future. I'm assuming when you say these are decommissioned wells, these aren't wells that were drilled last year or last decade, but they may be 20 or 30 or 40 years old, right? So the technology most definitely, from when I started working for Schlumberger nearly 30 years ago to today, has significantly changed. And it continues to become better. I mean, again, as I mentioned earlier, I believe that the application of these technologies, if you were to do the same well in the same environment today using most latest technologies, you end up with a better environment that you ended up with before. You know, what those regulations I think ultimately look like, I think it's going to be up to the regulators in Northern Territory. And you know, I cannot comment about what they should ultimately look like to prevent this type of thing happening.
The difficulty is that you said that you believe, and we're looking for evidence. The community has beliefs too, and those beliefs are sometimes quite diametrically opposed to your beliefs, and we're here in the middle trying to sort of get a position. And if you're not prepared to make suggestions, then who is?
Yeah. Again, I mean, there's no way for me to tell you what that needs to look like. I mean, you know, we can't by design dictate what those regulations would look like to make that happen.
You can't dictate, but surely you can suggest solutions. I mean, surely you can suggest solutions, because otherwise it may well be that a recommendation, an unfavourable recommendation is made by this panel on the basis of an absence of any data or evidence or techniques or recommendations coming from industry. And so far we keep having industry giving us quite bland statements of it's not for us and, you know, so on. That is not helping.
Right, I understand that.
Could I just add to that? You rightly keep making the statement about proper use of technology. We probably agree broadly with that, but it is what is the proper use that we're trying to scratch out here. So you might not want to comment on regulation, but surely to goodness you can tell us, in the case of Vaughan's question about abandonment and leakage of methane, what is the best technology at the moment that we should be looking to ensure, if the industry goes ahead, is put in place?
Yeah. I mean, so my recommendation is that you talk to the folks who have a vast experience with regulating those types of environments. Remember that you're in North America, you're dealing with in excess of 30,000, 40,000 with Canada wells per year that are being drilled in the various jurisdictions, and they have a long history of doing that. And that, you know, the regulations have continued to evolve from what they were, you know, 30, 40 years ago to something that is addressing the contemporary applications today. And I think, in my personal perspective, not from Schlumberger's perspective, is that they're probably the right entities to visit with. What are the things that you've seen that have worked best to solve these various issues? But again, remember, I mean, from where I started 30 years ago, the technologies have continued to evolve. How we do things have continued to evolve. And 30 years from now, they're going to look different again. But they continue to address the biggest issues that we're being faced with.
Our position at the moment would be, on the basis of the evidence, we could get to the point where we could recommend that there must be universal perforation and squeezing of cements on the basis of the evidence that we've had.
Yeah. Well, you know, again, I'm not familiar. I don't think that there's enough wells, first of all, for me to be able to draw a conclusion that would be the proper thing to do in that specific environment. It may be something that is unique to that reservoir that paper said. Maybe there is a shallow play that is highly charged that is pushing the methane to the wellbores. And the wellbores are just acting as a more conductive pathway to the surface than the natural matrix of the earth. I don't know. I can't answer that question. But I believe that the application of regulations should be specific to the environment that you're working in, because otherwise, you know, they become something that is, well, why are we doing this? And well, because someone halfway around the world in a completely different type of horizon was doing that.
Appreciate that. Okay, thank you.
If I may,
Yes.
I not necessarily agree that current regulations they're not working. For example, if cement is not adequate, our clients they're not allowed to produce a well, to operate a well, say in Queensland. That is the situation.
Sorry, they're
Be-
not allowed?
They're not allowed to produce a well unless cement is adequate, and they would have to do a remedial job to restore cement integrity. And to your question, so what is the technology for the abandonment? I recently presented a case in Darwin from North America, where they had high H2S content in a gas, and a well was located in the vicinity of a school. So they use a cementing technology Joe described it, which was like a self-healing cement with flexible properties, and that was successful. They put several plugs, and there are no issues. So they use it on a number of wells. I can provide you further information on this.
I think that would be useful if there are some papers that are in the open literature that can describe this self-healing properties of cement and the performance of such cements. We would welcome details of that literature. So, if I may move on. Second question, to do with rigs. You mentioned 30,000 rigs or wells are being drilled in the United States, and just interested to sort of get an indication of how situation will develop in Australia if we get into the production stage. And at the moment, as I understand it, there are only a handful of rigs in Australia that can drill horizontal. So, and given the demands that are going on in the United States, is Australia going to be left with only a couple of rigs, or how can Schlumberger sort of build up to the capacity of getting up to, I don't know, 50, 100 rigs, wells drilled per year?
We have rigs sitting around now.
You have rigs?
Yeah.
How many?
In Australia?
Yeah. They're not all deployed now.
So can I ask how many?
Oh, the exact number's changing on a day-to-day basis, but we probably have 5 drilling at the moment,
Right.
and probably it's 3 or 4 that are stacked, not operating.
Capable of
There's
doing
and industry overall, there's many that are stacked. Yeah, there's an
capable
excess of rigs at the moment.
of drilling horizontal wells?
Not all of them are.
No.
There's and it's also the depth
Okay.
and
So
reach.
my
Yeah.
question is, then, in order to be able to meet some of the projections that have been given to us in terms of, production in terms of drilling wells, is there and will there be sufficient drilling capacity in Australia?
So again, there would be significant technical gateways for the operating companies to get
Understand that.
through, and then plugging that into their commercial model. And if that stacks up, we will get rigs available depending on the commercial outcome. Okay, would be the short story. It'll be the economics of the overall development of the project, if it is significant, which remains to be seen. Don't have enough data at this point. The same way that we ramped up for drilling activity in CSG, I anticipate that we can do something similar with a different rig spec and design. It will be a completely different logistics story. Be some very remote operations. And look, we're a service provider. We enjoy that kind of operating, in that it's more challenging, more difficult, and that's kind of what we do.
Thank you.
Yes, Dr. Anderson.
Yes, thank you. I've got a question about well pad spacing, and it's in the context of community concerns here about risks of industrialising what are currently iconic Northern Territory landscapes. And obviously, distances between well pads is a key determinant of landscape transformation. And Mr. Lima, you talked about well pad spacing in your diagram of regulation evolution. And I was wondering if you could give us some information about the extent to which there are minimum spacings between well pads in regulations in different jurisdictions, and just where things are at in
Right.
North America. For that.
So it depends on the type of reservoir, but obviously the tighter the formation rock that you're trying to produce from, typically the closer that you end up with parallel wells. Okay, so the spacing, if you're not draining very effectively, you essentially add more wells to it. The U.S. experience, I think, is a little bit different than what you would see in Australia, from the standpoint that much of the land is being leased, and you have to, hold production or hold the leases by producing from a given area. So in some instances, you end up with, early on, one well and then another well not very far off, but basically helping to hold the lease from a production perspective. I've seen operators working in the U.S. that when they've had the land leased up and so on, and they get into a development process, they basically work this kind of like somewhat of a factory, and I know that term could probably make people nervous, but the idea is that you're working systematically across a play. So instead of drilling some wells all over the place and to hold the production, hold the lease, you'd actually work your way across this play from, let's just say, from the east over to the west, and that you end up drilling so many, building pads to do so. What's common today, the vast majority of the wells that are being drilled in the U.S., I think it's in excess of 90%, are either horizontal or they're directional in nature. So vertical wells are the minority today, where 15 years ago that was what you normally saw happening. With that, the ability, like that one image I showed you underneath the city of Greeley, Colorado in the U.S., the ability to go out there and start a project by putting locations off in different places and drilling out underneath these places to stay away from the places where folks don't necessarily want to see us development happen on the surface. We see that happening more and more. So we've seen like drilling underneath the airport in Dallas-Fort Worth, but obviously off from the side and drilling out underneath and so on. So that development, there's lots of opportunities. Directional drilling has allowed us to be very creative about how you place these. Now, there are some other things that constrain what this development looks like. Namely that if you were to drill, let's just say, a well site with 10 wells on one common pad, is that typically you're not going to go out there and drill and complete and get them all producing at the same time. The reason why is because you have to build your production facilities to accommodate the peak production on all 10 wells, as opposed to going out there and having a smaller facility that can accommodate lesser production, because remember, you have a natural decline on a well's productivity. So all these things go into the philosophy on how you're going to place wells. Typically with horizontals, what we see happening is anywhere from 2 to 20 wells on the location. And they typically will obviously go, you can drill, let's just say, off to the south in one set of wells, and a completely unique set of wellheads that are, and well bores that are drilling off in 180 degrees other direction. And there's also, the advantage that all the production for those wells go to one location. So that's typically what I think you're going to see happening. Again, as far as the spacing of well to well, it's going to depend upon how effectively you're producing these things. Typically, you might see that spacing starts out, let's just say, for argument's sake, starts out at 160 acres, spacing between wells, to where you get down to eventually 20-acre spacing as the field continues to mature, and you get an understanding about interference from a production perspective between existing wells.
Yes, I can understand that there's all sorts of technical and commercial factors determining the spacing, but I was thinking more in terms of regulation in the context of avoiding major landscape transformation from an amenity perspective. And so I guess my question is very specific about, is that regulated? Are there examples of where it's regulated in that context
I
or
have
not?
not seen examples where that's required. I know that you shall do it this way and so on. but I see that that's happening in practice, okay? So even most of the operators, there's one operator that I work fairly closely with that sends its engineers to a potential location at night to see if if the headlights shine through people's houses. So, you know, that philosophy, even though the regulation doesn't say so, the philosophy exists that they're trying to minimize the impact on stakeholders, whatever they are, whether it's, you know, wildlife or it's a community that's being engaged. But I can't think off the top of my head, I cannot think of of one that specifically says, don't, you know, you can't drill over here and so on. There are some requirements in urban environments in North America around distances, you know, setbacks from homes and schools, that type of thing. And there's also some requirements around things like noise and noise levels.
Yeah, thank you.
Gentlemen, we are wildly over time. Thank you for being patient. Part of the reason why that has occurred is because I appreciate that you've come a very long way. Some of you have come very long ways to attend here today, and we're very grateful for the time that you've given up in the presentation. We'll be able to get a copy of those slides.
Yes.
Great. But again, thank you very much for answering all of our questions the best of your ability, and we appreciate your time. Thank you.
Thank you.
Thank you.
Thank you.